All right, here we go. Close them up, have a look. Steph, come closer. Get where you can see this. Okay, so what if we wanted to answer the question here? Now, we don't want to use our old cumbersome vector methods, but if we want to find the speed of the package after the push, how could we do that?
On the acceleration?
I know, we don't, that's what we're going to not do. Because we don't want to use kinematics. We want to see if we can do this in a new way, in an energy way, work energy way.
Asking us to see a different dimension.
What could we do?
Right, work is force over displacement. So
Work is force times displacement, right?
So it's being displaced 0.8 meters.
Good.
With a net force of 115.
Okay, good. So we could. There's two ways we can do this. We know what we're going to utilize here is the work energy theorem, right? We know that the net work is equal to the change in kinetic energy, right? So the net work, how could we think about that? Well, we could separately calculate the work due to all of the forces. These two forces do no work, right? Yeah. Because they're perpendicular to the direction of travel, to the displacement. But we could separately calculate the work due to the push and the friction, and then add up those, or better yet, we could just identify what the net force is, and these are going to cancel. The net force is just going to be 115 to the right. Everybody agree?
Yes.
We add all those vectors up. So net work then would just equal net force times displacement, right? Which is 115 newtons times 0.8 000, I should probably put those, 000 meters, gives us how many joules? What's that going to be? Somebody help me out here. So, 800, so 92. 92?
Yeah.
92 joules, 92.0 joules, right, is our change in kinetic energy. So let's assume that this thing started from rest. I guess I should probably put that, starting from rest. What's the final speed going to be? Okay, so how can we do that then? If it starts from rest, what's the initial kinetic energy? Zero. Okay, 0, and so final kinetic energy must be 92, right? 1/2 mv squared. Yeah, exactly. So 1/2 mv squared equals 92.0 joules, wow. Right? Easy, way easier. All we got to do is multiply by 2, divide by the mass, and square root. So speed equals 2 times 92.0 divided by a mass of 30.0. And what's that give us? Somebody, after 3 plus.
Don't you need the square root?
Oh, yeah, square root, yeah.
And that's about 2.48.
2.48?
Yeah.
Is that what you got?
But you just square root the whole time?
Well, yeah, you must have, because that's 2.92 divided by 30, and then square root it.
184 divided by 3, so that's about 6 point.
Square root is going to be, yeah, so that's about 2.4. I think 2.48 sounds good. It'd have, yeah.
Did you do something wrong with that? Oh, it's 62.
So now what if we change this problem and we said instead V naught equals 2.11 meters per second? What's great about this is the change in kinetic energy still would have been the same, right? Does that make sense? So it doesn't matter whatever we start with, the change in kinetic energy, like, see if you can spot a shortcut here. So my initial kinetic energy would have been what? 1/2 m times that squared. So initial kinetic energy would have been 1/2 times 30.0 times, here, let's make this a better number so it's not so hard. Let's just say 2.0. Times, right, so we would have gotten what, 15 times 4, so 60? 60 joules would have been my initial kinetic energy, right? So if I were to add to that, my change in kinetic energy was 92, right? Because that's by the work energy theorem, that's what it is, right? We know that net work equals change in kinetic energy. So if this had had some initial velocity, but I applied a force regardless of what the initial velocity was, if I applied a net force of 115 newtons through 0.8 meters, the change in kinetic energy is the same regardless of what my initial kinetic energy is, right? So then my final kinetic energy would have ended up being my initial kinetic energy plus the change in kinetic energy, right? Which would have been 60 plus 92 is 152, right? And I guess I'm adding, so I would have kept that 0, right? Kept the point 0. Make sense? And so if we do the math on this, well, it's the same math, isn't it? We would have ended up with the same formula. Speed equals the square root of 2 times my kinetic energy divided by 30. So what's that equal to?
3.18. That's what I get.
3.18? Okay. Okay, does that make sense? Okay. Okay. See how that works? Okay. So all we would need to know is whatever the initial kinetic energy is, we're gonna add that amount to it. That seems a little funny to me. Oh, I know why.
Huh.
Yeah, that didn't work. That didn't work. Because why did I put my initial kinetic energy was not 92?
Good one.
No,
That's the net.
0.
it was 60, right?
Oh, right. No, 92 is your chain.
It was my change, right, okay. It was my change in kinetic energy. Because that was the net work, right, okay. So we have that up right, 60 and 92 is 152. Yeah, okay. So, square root of 2 times 152.
Yeah, that's just,
You got 3.18 on that?
think about that. 15 on the bottom, 150 on the top.
Yeah.
It should be 10.
About, that sounds about right, because the square root of slightly over 10 would be about like that.
Yeah.
So that makes sense, okay. Was this right?
Why do you think it's wrong?
I just doesn't seem, the numbers don't seem right to me. It just doesn't seem right, so.
It's about the square root of 6, so it should be about 2.5.
And
Should
the
be the
initial
square
kinetic-
root of
6.
6, yeah, I guess that's right. Yeah, I guess that's right. Okay, I guess it just didn't seem right to me. Okay. Right? Anyway, so we see how we can use the work energy theorem, which is arguably a little bit easier than having to deal with all the kinematics equations and the vectors, right? Okay, we can do this all in terms of energy arguments. Okay, how about this one then? Oh, and this just, I was going to go through this, but I'm not going to. I don't think we need to. This was just going to be a demonstration of how we could calculate the net work in 2 ways. I'll just show you real quick, and I'll put these in the notes. If you want to look at them, go ahead. So we could use, like we did, we could use the net force of 115 times 0.8, we get 92 joules, right? So that's the net work done. Or, if we wanted to, we could also, as we previously mentioned, we could find the work due to all of the individual forces the work due to the push is 96 joules, the work due to friction is -4 joules, and the work due to the normal force and the weight are both 0. And so if I add up all that work, I end up with 92 joules, right? Either way, I'm going to get the same result. Which way is better? First way. A little easier, right? Okay. Try this one. Okay, there's some good physics, everyday physics going on here. So the force needed to bring a 950 kilogram car, that's a pretty small car, to rest from a speed of 90 kilometers per hour in a distance of 120 meters. So that's kind of a non-panic stop. Calculate the force needed using work and energy arguments. Okay? Do that real quick.
How much is average car weight?
Well, 1,000 kilograms would be 2,200 pounds.
Oh,
So that would be small. That would be small. My truck, I know, is ridiculous. It's like, well, probably almost 3 tons. So it's,
oh.
but a car would be, what's your car weigh, Nick? You probably know.
Mine's pretty heavy, mine's 2 tons.
Is it really?
Yeah.
Wow. And that's not a super huge car. I mean, so I'd say probably around 2 tons is average.
Oh.
Yeah. All right, y'all set?
Can I do the third one, or do you want me to?
Let's do it tomorrow.
Okay.
Yeah. Okay. So be thinking about this. How are we going to do this calculation? We should be able to use the work energy here. What's the final kinetic energy? 0. Okay. So what kind of force is this that we're talking about? Friction. Okay.
Is that just 90.0 in the right?
90.0, yeah.
Why don't we ever measure in decagrams?
In decagrams?
Yeah.
You could.
Weird. But no one does that.
No.
No one even really acknowledges the deca part.
We just
of the
use-
metric system.
What's that?
No one even really acknowledges that part of the metric system.
No, I know. People, right, exactly. No, we just use milligrams, grams, kilograms.
Thanks to Mr. Johnston.
For a base 10 system, there's a lot of thousands used.
Yes. There are, I would agree.
How small is that ring is?
Oh, yeah, we should probably,
Which mass? No, I'm good.